We should actually save your applause for Rick because he's the main event here tonight. But first of all, thank you for coming. We're really looking forward to telling you all about the Juno mission and frankly the incredible and exciting engineering that got us to Jupiter and some of the science that we'll be conducting there as a part of the mission. And it really is historic and groundbreaking and I would say truly an amazing technological achievement. And Rick will talk a lot about that. I usually like to just open and make sure you understand why we call this the William Pickering Lecture. I assume most of you know, but many may not, that Dr. Pickering was the first director of JPL. And so we honor him with this lecture series. He took over JPL in 1954. So as you think back, well before Sputnik and all those things that happened, and really led JPL and ultimately the NASA team through an incredible number of historic firsts, responsible for America's first satellite, Explorer 1, also responsible for the first mission to another celestial body, Ranger, the Ranger missions in the mid-60s, then responsible for the first landing on another celestial body with the Surveyor missions, the first visits to other planets, both Venus and Mars with the Mariner missions, and then the first landing on another planet with the Viking mission in 1976. So just an incredible man, and if you look back to his speeches in 1962 and thereabouts, the vision he set for JPL and in many ways for NASA in terms of planetary exploration are still true today. The words he said exactly apply today in terms of our vision and what we're all about from a planetary exploration perspective. So just an incredible man, and we honor him tonight with that. And so you're going to hear about, again, one of those incredible explorations of another celestial body in our solar system, obviously Jupiter. Rick will talk about the challenges of Jupiter, and they are incredible. Rick has been the program manager since 2012, and that's roughly about a year after it launched, as I do the math. Before that, he was the deputy program manager. So he has been on Juno for about 10 and a half years. So it's kind of his baby, a long gestation period, finally giving birth on July 4th in terms of actually reaching Jupiter. And a truly exciting time, and I'm sure many of you saw that or watched a part of that versus on the internet or NASA TV or whatever the case may be. Rick has also had a tremendous amount of experience in executive leadership at JPL. He's been on the Magellan program, Galileo program, a whole host of key projects there at JPL, and has been a tremendous leader in the Juno mission and getting us to this historic first. So Rick, with that, we'll turn it over to the main event, and thank you all for being here.
Well, thank you. I'm really pleased to be here, and I'm really pleased we're finally at Jupiter. It's been a long road. So Scott Bolton was going to join us tonight, but unfortunately he had to stay in Texas due to personal issues. So I'll walk through everything here. But you will see his picture in some of the videos, and you'll hear his voice. So he's here in spirit. So Juno is a mission. I like to think of it as a mission of daring, innovation, and discovery. Daring because we're going to the most hazardous planet in the solar system, operating deep within its radiation belts. Innovation, because we had to design a mission in a spacecraft that would survive those incredible radiation levels. It's also the first solar-powered mission to Jupiter, so we had to do a lot of creativity and innovation to make that happen as well. And discovery, you'll see that we have an incredibly robust science payload. We have 9 different science instruments, 10 different science investigations. This is a science bonanza. And the science that we're going to get during our mission to Jupiter is probably going to rewrite the textbooks about how Jupiter formed and the history of our solar system. But before I get too deep into it, let me back up and take you back about 5 years to when our journey started.
This is Atlas Launch Control. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Juno spacecraft aboard an Atlas V rocket. Liftoff is from Launch Complex 41 at Cape Canaveral. The forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria.
It takes everything we know to get off this planet. So while everything that NASA does and building the Juno spacecraft and exploring Jupiter is all high tech, I think a rocket launch represents the extreme of that edge.
The energy in the room on launch day is stressful, but in a good way. It's a good feeling. It's almost electric. Everybody's excited and nervous, and I've seen people before, biting their nails.
A rocket launch is one of the most amazing things to see. I mean, it's truly a cosmic event.
OSM.
Go.
ULA safety officer.
Go.
Range, weather, and final clear to launch.
Go. LC, LD, channel 1.
Go ahead.
LC, you have permission to launch.
Roger.
A launch is probably our single biggest risk in the entire mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
When you see it, the first thing that you're impressed with is just the amount of energy. You feel it because the ground is shaking and you're miles away and the waves are coming through the ground like an earthquake would.
Mach 1.
You're canceling gravity. Gravity's pulling you down. You've got to get to a certain speed, and then that's the escape velocity to leave the Earth.
Max Q. Boosters throttling up. We're on schedule. Engine response looks good.
You're watching something going from one planet to another.
And we have solids 1, 2, 3, 4, and 5 jettisoned. Visual indication that all solids have separated well. Current altitude is 45.8 miles. In altitude, downrange distance 69 miles. Velocity 5,413 miles per hour. And we have payload fairing jettison and CFR jettison. We have retros and spacecraft separation. This concludes the plus count commentary for the AV-29 Juno mission.
That's really cool. I think one of my favorite things there is to always see the view from the rocket cams. It's just something amazing when you get to see the rocket take off and Florida disappear behind you. So let me tell you a little bit about the mission. We're the first solar-powered mission to Jupiter. We are a spinner, and I'll talk a little bit more about that as well. We're also a polar orbiter. The first time that you investigate a planet or you visit a planet, you'll probably do a flyby. The next time you do a more in-depth investigation, you'll do an equatorial orbit so you can study the entire system. But when you really want to study a planet up close and personal, polar orbits are the way you do it. That's what we do at Earth, and that's what we're doing here. And you can see that we go between the planet, the cloud tops there, and the radiation belt peak. That bright spot there is unsurvivable. We still stay well away from that. And it's about 2 hours from pole to pole. So from the North Pole to the South Pole is about 2 hours. We launched back in 2011, as you saw. We arrived successfully on July 4th. I'll show you a little bit of that. We do 32 science orbits, and then in February of 2018, we'll deorbit into Jupiter. Now, you might have the same question I did. Why are you going to do that? If the spacecraft is healthy, why don't you just keep operating? A lot of NASA missions do. And we certainly design the missions to have a very long lifetime. But there's a moon, Europa, that has an icy crust, and it's believed to have a liquid ocean and maybe life underneath, and they want to make sure that we never contaminate Europa. So it's a planetary protection consideration. It's a requirement imposed on us by headquarters to make sure we have a less than 1 in 10,000 chance of ever hitting the European moon. So right now our plan is to deorbit February 20th of 2018. There's a trick we have up our sleeve that I'll talk about later. We might get a few more months out, but it's a little tricky given the deorbit requirement. So this is the Juno spacecraft. The first thing that jumps out at you here is the immense size. This is roughly the size of an NBA basketball court. We needed to do that because the sunlight intensity at Jupiter is only 1/25 of that at Earth. So we actually are using commercial solar cells from Spectralab at Silmar, 18,698 of them. And we tested them under low intensity, low temperature, and radiation conditions to make sure we knew how they performed, because they're certainly not designed to perform under radiation and way out at Jupiter. With that information, we were able to size the arrays to give us over 500 watts of power at Jupiter. Now that creates another challenge because we flew by the Earth. And when you fly by the Earth, these arrays would produce over 14,000 watts of power. So we actually had to turn off most of the arrays just to protect our critical electronics. The other thing that really jumps out here is our science payload. We have 9 different instruments here that perform incredible science. Gravity science is arguably the largest instrument in the solar system because half of the instruments on the spacecraft and the other half is on the ground at Earth, the Deep Space Network. We use gravity science to help understand the interior of the planet. It's an X and K band dual frequency system. We also have a magnetometer out on the end of the boom there. On the lower right-hand corner, you want to keep the magnetometers well away from the spacecraft. We have a 6-channel microwave radiometer, so that 6 receivers that pick up the energy that's emitted from the planet. And we're going to measure the water abundance, which is going to help us understand where Jupiter formed. JEDI, JADE, and WAVES are all fields and particles instruments. You could kind of think of them as connector instruments in a sense because they help us understand how the magnetosphere connects to the planet itself and the auroras. They measure the electrons and the ions in the electric field. They help give us the whole story in an integrated manner. And then at the bottom there you can see we have an ultraviolet camera, an infrared camera, and a visible light camera. And I'm going to show you some images from those of Jupiter later on this evening. So, how bad is the radiation at Jupiter? We've been talking about how it's the craziest place, it's the most hazardous planet in the solar system. Maybe a good way to explain it is to talk about what we see at Earth, first of all. What you're exposed to here over the course of a year is about 1/3 of a rad. What's fatal for a human being is about 1,000 rad. What Juno's going to be exposed to over the course of our mission is 20 million rad. So if we didn't do something very effective, we wouldn't last more than one orbit. So what we chose to do was to put our critical electronics inside a protective vault, a radiation vault, with walls of solid titanium up to 1/2 inch thick. This is really unusual because titanium is a very heavy metal. This vault empty without any of the electronics inside weighs over 400 pounds. But it was a necessary step and it's a very effective step. It reduces our radiation by a level of 800 to 1 inside the box. Here you can see the vault being lowered down on top of the spacecraft. This is very early in the integration. The module on the bottom is the propulsion module. You can see the fuel tanks there. What's underneath on the bottom is the main engine. So we really don't have much of the avionics or the instruments or the communications gear on. We're just putting the core together at this point. This is a fully integrated spacecraft. You can see the high gain antenna at the top. Underneath that, you can see the radiation vault. It's about 1 meter cubed. On each side, you can see the stowed solar arrays. The one on the right is where we have the magnetometer boom, so it stands a little taller. And what's facing you there, you see those flat panels are microwave antennas. Those are planar arrays. There's 4 of them there, and there's actually a small horn right next to one on the top deck. There's one more, and it's around the other side of the spacecraft. That's the lowest frequency, the largest antenna for the microwave radiometer. The size of that one antenna dictated the size of the entire spacecraft because it's so large we had to make sure it would fit. One other thing I wanted to point out here on this slide, this is a spinner. With this amount of instruments, you can imagine the scientists are all elbowing each other trying to figure out how are we going to multiplex the viewing time. There's 24 sensors that all want to look at Jupiter. And one of the advantages of having a spinning spacecraft is we can multiplex all the sensors around the edge of the spacecraft. That simplifies operations. They look out in between the solar array wings there. And it's a good way to also look at deep space. You can look at the synchrotron as well, which I'll tell you about in a few minutes. So it's one of the concepts that helps us integrate and effectively operate such an incredible payload. So this is another shot. You can see that we're carrying some special passengers along with us. These are LEGO minifigures, Galileo, Jupiter, and Juno. We have a Danish connection as well, so there was a natural connection with LEGO. And you're probably wondering where our name came from. Well, Jupiter had a reputation that his wife was well aware of. He would go down to the Earth's surface and get into some mischief. And so he would cover up that mischief with some clouds. His wife knew something was up, and so she was also a goddess. She would peer through the clouds to see what Jupiter was up to. And in a way, that's exactly what our mission is doing, and that's why we're named Juno, because all of our instruments do remote science. We don't have a probe, so we don't send anything into the planet. Everything we're doing to study the interior of the planet, the exterior, the magnetosphere, is all done remotely. Here you can see we're getting closer and closer to launch. On the upper left picture, this is the final deployment test after we install the solar array wing 2. And on the right-hand side, of course, we have to do a final illumination test to make sure all the connections are working properly. On the left, this spacecraft is just about ready for launch. You can see there's still some protective covers there. Those red covers at the bottom and also on the microwave antenna are removed before flight covers. The reason I left this picture in here, though, is it reminds me that we had a very interesting thing happen because we have a magnetometer. And it was something that caused us a lot of concern initially, but the lead scientist for the magnetometer, about a year before we started serious integration of the spacecraft, came to us and said, you know, we need to do a swing test. I said, a swing test? What is a swing test? He said, you lift up the spacecraft, and we swing it back and forth so we can measure the magnetic characteristics. We said, are you crazy? There's no way we're going to let you do that to the spacecraft. This is $1 billion spacecraft. He said, look, it's very difficult to characterize accurately all the magnetic features of the spacecraft, and they have to be able to back that out when they're in orbit, because inevitably you have we have some magnetic material flying on the spacecraft. And it's difficult to measure the magnetic properties of spacecraft when you're in the magnetic field of the Earth and also the magnetic field of your building. And so we eventually found out how we would do the test. I think we over-designed it. I think we used a 10-ton cargo strap to lift a 1-ton spacecraft. It's only about 1 ton when it's unfueled. But it's still a very nerve-wracking test to see because we had to pull it to the side about 10 feet. The technician cut the tether. And this 1-ton spacecraft, $1 billion on the end of a single tether, swung back and forth 10 feet each way. I got a speeding ticket driving home to the airport that night. But we got everything we needed out of the test, and the Mag-Co-I was happy. And remind me never to fly a magnetometer again. Oh, the picture on the right there was actually really good and really sad in a way. What you're looking at there is the last time that we ever saw our spacecraft. All the removed before flight covers have been removed. It's in full flight configuration. The tall object on the left is the payload fairing. When you launch on top of a rocket, you have to encapsulate the spacecraft in the fairings to protect it from the atmosphere as you accelerate up. So The good news here was we're very close to launch. The bad news is this was the last time that we ever saw our spacecraft. On the left here, the spacecraft is fully encapsulated. It's been transported through that really cool transporter all the way out to Space Launch Complex 41, the vertical integration facility, getting ready to be pulled up and set on top of the Atlas V launch vehicle. And on the right, you can see the launch that you just saw a video of. So after we launched, we had enough energy from the Atlas V vehicle to take us out past the orbit of Mars. And there we conducted 2 deep space maneuvers, also known as firing your main engine. We didn't want to fire it for the first time at Jupiter, and so we actually got 2 practice runs here, and they went perfectly. And those 2 main engine firings accelerated us back around the sun, past the Earth, got a gravitational assist from the Earth flyby that added 70% more energy than the launch vehicle gave us. That was enough energy to get all the way out to Jupiter's orbit, and we arrived there just this year on the July 4th. But the Earth flyby is kind of interesting if you think about it. We flew over the south portion of Africa. The lights on the left there are Cape Town. You wonder whether you can see something. We flew by pretty low, about 500 miles above the surface. And there were a number of amateur astronomers that got images of us. You can see one there on the right. But we had kind of an interesting discussion. Is there anything we could do on the Earth, maybe, to say hello to us passing spacecraft? And some of the people on the team came up with a really clever idea, and we wanted to share this with you.
This is my transmitter. Maybe it's something you can use, I don't know.
The High Juno experiment is something that a group of us came up with.
The biggest challenge we had was we didn't know if this was going to work or not.
If it works, you know, I'm part of history.
This is W6JPL, Jet Propulsion Laboratory in Pasadena, California. Hello, CQ, CQ, CQ.
The Earth flyby is Juno's way of gaining some extra speed and changing direction so that its orbit can take it to Jupiter.
There he is with us.
We said,
That's our principal
what
investigator.
if we actually sent something to Juno? Basically came up with the idea that we could send Morse code to Juno, enlist the support of amateur radio operators around the world.
So the intent is to join amateur radio community together in a coordinated transmission from Earth to the Juno spacecraft as it flies by.
The website would tell them, okay, key down now, then key up, transmit for 30 seconds. And that's how we would send a DIT. Everybody knows Morse code is dit, 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 da, da. Well, it turns out to say hi to Juno, it takes 4 DITs, a space, and then 2 DITs for the eye.
I thought, wow, that's a neat thing to do, and they're going to need a lot of people to pull this thing off. I said, I'm good to go.
We're getting ready right now. Here we go.
And now we are transmitting here.
They could hear ham radio operators all over the world doing this, which was really remarkable.
Everybody's doing this at the same time. Thousands and thousands of hams.
With any luck, the Juno spacecraft will be able to listen and hear all these amateur radio transmissions.
And so what we're doing now is we're looking at the data that's come down to see if we can put together that signal that says, hi.
Will it work? Who knows?
I have the audio from Juno. I'd love you to listen to it.
This sounds very cool.
And it actually worked, and it heard us.
When you think about what it is, it was really, really amazing.
How many times do you get to say hi to a spacecraft that's flying by your planet? To be a part of it, that was very great.
More than thinking about what it means to me, I think it's just such a great thing that humankind has the ability to think beyond our own environment. It's the curiosity, it's the adventuring spirit, I think, that the space program has given us.
Hi, Juno!
Hi, Juno.
Hi, Juno.
Hi, Juno.
Hi, Juno.
Hi, Juno. Goodbye, thank you.
Okay, take 17.
It's one of my favorite things that the team did during cruise. I mean, how special is that? We have thousands of people around the world that are able to, in effect, communicate with the spacecraft and say hello. And we saw it with our WAVES instrument. The same instrument, you're going to see some more data coming up on later. So a couple years after that, we're getting close to Jupiter. So this is an engineering diagram. Apologize for that, but it is kind of interesting because it shows you the last 6 months. So what you can see when you look at this is it starts on the left 180 days out. And by the time you get all the way to the right, that little tiny dot is Jupiter. The red lines there are the orbits of the Galilean moons. And this shows the various activities that we go through as we approach. So in purple, you see TCMs. That stands for Trajectory Correction Maneuver. And our mission, our journey to Jupiter is, we flew almost 1.7 billion miles. And we build in TCMs to allow us to fine-tune our path. Now we have the advantage, of course, in 5 years, we've really gotten to know how our spacecraft operates really well. Especially, it's critical to understand the small propulsive maneuvers. And you couple that with a world-class interplanetary navigation team. And what happens is, in the end, we have to hit a 10 by 40 kilometer window within about 5 seconds in order to enter Jupiter's orbit correctly and start the main engine firing. So these TCMs are what we use to fine-tune our course as we came in. Turns out everything was working so well. The last TCM that we had to do was TCM 11 on the left there, 5 months before we arrived. You can also see on the bottom right, the yellow square and the blue rectangle there. Those are the regions. The scientists kind of had a little pool going because they didn't know exactly where they would cross the bow shock and see the magnetopause, and I'm going to show you a little bit more about that. So that's why it's a range. But once again, we've got some really interesting data that we want to share with you from the WAVES instrument when we cross those two epochs. So now you know what space sounds like. And I can tell you the space at Jupiter is among the most interesting. We're going to make recordings of a lot of the different orbits ahead of us, and we'll share those with you, so you need to follow along because some of the waveforms get incredibly interesting. You don't want to drink and drive after seeing some of these waveforms. So now we're getting down to payday. Jupiter orbit insertion is the most important and critical event that we had on the mission. On July 4th, we had to fire our main engine. We had to turn the spacecraft, because our rays are always facing the sun. We had to turn the spacecraft off sun and fire the main engine in just the right direction to slow us down so we could get captured into Jupiter's massive gravity field. As big as that planet is, as massive as it is, we were still had too much speed and we would fly right by. So we've been preparing the spacecraft for a couple of weeks. There's a lot of very intricate things you have to do in terms of the prop system setup. You fire the latch valves, you have to warm the tanks up, you have to do it in a particular sequence. By the time we got to this day, everything was set up perfectly. All that was left was the turn, spinning up to 5 RPM, and the 35-minute burn. And then, of course, after that, we have to spin down and turn back to sun because we need to get back to sun if we're going to live. And the interesting thing about this, and I'm going to step off the podium for a second so I can show you. The interesting thing about this is the main engine burn starts right here. This is the radiation belt as it circles most of the planet. So the most intense part we miss because we fly under, but we still fly through these horns. And over here, it's these horns right there, above and below. So when we took a look at where the peaks of radiation were and where we fired the main engine, we found out that we start the main engine burn right at the first peak of radiation, and we finish the main engine burn and have to turn back to the sun right when we go through the next peak. So the most critical event that we have to undertake in the whole mission had to occur at exactly the first time that we go through these intense radiation fields. So that made that night a lot more interesting. It was so tense I couldn't sit down. How did it go? It actually went very well. You can see on the upper left, those of us there's Scott, the principal investigator, and a bunch of us in the Pasadena Mission Support area there at JPL. Lockheed Martin built our spacecraft, and half of our operations team is over in Denver, so the picture on the upper right-hand corner is the operations team in Denver. Times Square celebrated along with us in the center. Google even got into the act. So it was a great night. But it's important to point out that this was just a gateway. There's a tendency, especially for engineers who build spacecraft, to think, this is really so cool, but the cool stuff's still ahead of us. We've still only done one pass by the planet. Let me show you what that looks like. So now that we're in orbit, this is what's coming up next. We're in a large orbit right now. It's a 53-day orbit, and we do 2 53-day orbits. After we complete the first one, we fly by the planet on August 27th. We've done that already. I'm going to show you some images from that. That's the first time that we turn our instruments on. Everything is really simplified when you fire the main engine. All the instruments are off, much to the scientist's chagrin. We turned everything on August 27th. Things worked really well. The reason we did that is we needed to get a preview. Since nobody's ever been this close to Jupiter, all we have are models, and we needed to make sure the instruments knew what they were going to be seeing when we got into the formal cadence of science orbits. And so that's why we did an early pass on the 27th. When we come back around one more time on the 19th, this will be when we fire the main engine for the 4th and final time. And at this point, that'll place us into a 14-day orbit. Now the radiation clock is ticking. Every time we fly by the planet, we accumulate radiation. So we have to make sure, in fact, we make the decision on Monday about whether we're ready to go ahead with this or not. Because at that point, you are locked in, and we only have 16 months to get all this data. And some of our investigations need every single orbit. Imagine that, having to get a successful pass, no computer resets, nothing. 32 times in a row. The other thing that's interesting, if you look on the lower left there, you can see that our orbit plane starts to shift. And you might wonder why. But Jupiter, it turns out, is a very interesting planet in some other ways as well. First of all, it's the largest planet in the solar system. We all know that. You can fit 11 Earths inside across Jupiter. It's 330 times more massive than Earth. But despite that, it rotates at an immense speed. It completes a full rotation every 10 hours. So this massive planet rotates more than twice as fast as Earth does. That actually creates a bulge. And so this planet is not circular. It's actually oblate. It's about 10% wider, the diameter at the equator, than it is at the pole. And that oblateness starts to pull our orbit around about 1 degree every time we pass by. So you can see that not only do we get radiation every time we fly really close to the planet, just above the cloud tops there, in between the radiation belt and the cloud tops, but as our orbit plane shifts, we will fly more and more through the outer portion of the radiation belt as well. And that's why we have a limitation on how long this mission will last, because the radiation, as I said, we'll see 20 million rad over the lifetime of our mission. 16 months. So you can see here we have the two, we came in from the top. You're looking at this from the sun angle, so the sun is out of the page. We came in from the top. We have the two 53-day orbits. We fire the main engine one more time and we get into our 14-day orbits. And you can see how the 14-day orbits slowly progress downward over our 16-month science mission. And on the right, you see the matrix, the web of orbits that we'll build. We will completely encircle the planet, making measurements with all 9 instruments. This is a computer model of the radiation belt that we flew through on August 27th. The thing that this makes me think of is a hurricane. So I think it's not unfair to say that our mission is like flying through the eye of a hurricane, only we need to do it successfully 36 times in a row. So why would we do something so crazy? Because of the science. So let me tell you a little bit about Juno science. The primary thing that we're after is the very top there, the origin. We're after the water abundance. The last mission to get to Jupiter put a probe down to the atmosphere, and they discovered the ratio of heavy elements compared to the sun. But there were a lot of questions that remained unanswered. The biggest single question that remained unanswered was how much water there is in the atmosphere of Jupiter. So they said, let's do a follow-up mission. It'll be a high science priority. It's in the decadal survey. They were asking people to propose a follow-up mission for a Jupiter orbiter with 3 probes. The probe back in '95, when it went in, got such a low water measurement, it blew all the theories about planetary formation and Jupiter's formation out of the water. So I think that the thinking must have been, let's send a follow-up mission with 3 probes. Well, we found a way to make that water abundance measurement not in one location, not in 3 locations, but globally over a 16-month period. To me, that is probably the signature innovation of this mission, to be able to do all that remotely and globally. The other thing that really ties to origin is determining whether or not we have a solid core inside the planet. The fact is right now, they don't know whether Jupiter formed where it is, formed closer in, formed farther out, and Jupiter has 2/3 of the mass. You can take all the other planets and the asteroids, everything but the sun, and throw it into Jupiter, and still, it's much, much larger than that. 2/3 of the mass outside of the sun is in Jupiter. So we know it formed first. We know that it had a huge impact back during the solar system formation. It continues to have an impact on the solar system today in terms of comets and asteroids. So understanding what's in Jupiter, the water abundance and the core mass, will help us understand where it formed. We also will investigate the interior structure of Jupiter through our gravity science and magnetic investigations. We'll investigate the atmosphere, and I'll show you another slide about how we intend to do that. And the magnetosphere, and how we have these incredible connections to these brilliant aurora. We can see the aurora with our infrared and ultraviolet instruments, and I'm going to show you some shots of those coming up. So this is an artist's conception of what the interior of Jupiter looks like. The first thing you should notice is on the left, you see 2 megabar and 40 megabar. 1 bar of pressure is the pressure that you get at sea level. This planet is so dense that you go partway through the atmosphere and you already have 2 million times the pressure that we see at sea level. This does some incredible things to the inside of the planet. Jupiter is mostly helium and mostly hydrogen. The hydrogen is under such pressure that it actually converts from a gas to a metal, a liquid metal. So you actually have liquid metallic hydrogen, which we can't make on Earth. You can't even see it on Earth. We don't have any way to create those kind of pressures. You have liquid metallic hydrogen that's circulating around this massive planet, and that is what they believe generates these huge magnetic fields and the radiation fields. And when I say huge magnetic fields, so they're most powerful in the solar system. The magnetosphere is so large, it's larger than the sun. If you could see it from Earth, it would be a little bit bigger than the moon. The tail of the magnetosphere reaches all the way out to Saturn. And we're flying through the connection points with just the perfect set of instruments to understand what that magnetosphere is composed of and how it's connected to the planet. And of course, our gravity science measurement will help us understand whether there's really an ice rock core. It's interesting, you see a question mark there under ice rock core because at those pressures, ice and rock would not be like anything you can think of or I can think of. It's just, it's like science fiction. Sensing the deep atmosphere, again, this is one of our key investigations with the microwave radiometer. Jupiter formed 4.5 billion years ago. It's still cooling. And the temperatures reduce as they come out, and we can use that to our advantage because we can measure the thermal radiation coming out of the planet at different frequencies, and that helps us understand the cloud structure, but more importantly, it helps us understand where the water is. When the Galileo probe went into Jupiter's atmosphere, it was designed to last to a pressure of 20 bars. It did everything it was asked to do. It lasted to 22 bars. The trouble was the atmosphere was not well mixed. They may have hit a dry spot, the Sahara Desert, so to speak, of Jupiter. So you have to go deeper. We're able to go down to 1,000 bars. And we'll do that globally. So we've already made one pass by the planet. The radiometer seems to be working as expected. We're very optimistic that we're going to get the data that we flew all the way out there to get. And the interesting thing is, why couldn't you do this from Earth? You can measure emissions from Earth. We take images from Earth. We have incredible instrumentation. Very large telescopes. We do radio astronomy. Well, the answer to the question is what you see moving around on the left there. That's something we call the synchrotron. So the synchrotron are radio emissions that come out of rapidly moving electrons that go up and down the field lines. So these electrons are trapped in Jupiter's magnetosphere. They're going up and down at the speed of light, and they generate radio waves that obscure the planet in terms of the radio emissions. So we couldn't get this measurement from Earth. More importantly, this forces you to go right next to the planet because you have to get inside that synchrotron if you're going to measure the water. So you really have to go just above the cloud tops. And then I had to put this in because this is the most beautiful, intriguing planet in terms of surface features. Look at those belts and zones. Some of them move as fast as 1,000 miles per hour. Most of you are familiar, I'm sure, with the Great Red Spot. The Great Red Spot was seen by Galileo over 400 years ago with his 20 magnification telescope. You can fit an entire Earth in the Great Red Spot. Yet for all this, we don't know how these incredible cloud features are generated. We don't know how deep they are. Our microwave radiometer is going to be able to not only look straight down to understand these cloud structures, but since we're spinning, we've got all these incredible side angles as well. So we're going to learn an incredible amount from the microwave radiometer about the atmospheric dynamics and the structure of the atmosphere and what creates these incredible cloud formations. Our visible light camera is something that everybody in this room can participate in. We've opened it up to the public. From the beginning, this was our intention that amateur astronomers, anybody in the public, can go to our website. You can upload pictures. You can participate in the discussions of where we should aim our camera. We can't take pictures of everything, so we'd love for you to participate in that discussion. You vote on points of interest. The raw images are all posted. They can be processed by the public. When we flew by the Earth, some of the images of the Earth were processed before we did it. Literally, we had a late night, flew by the Earth, it got up in the morning, and they were already posted on the mail-in website. So you can go to the Juno website and participate in this, and the funny thing is that if you're a Juno scientist, if you're on the team, and you want a picture to be taken, you have to go through the same process. So you get to rub elbows with some of our scientists. That could be fun. So we flew by Jupiter for the first time with our instruments on Perijove 1 back on August 27th. I wanted to share some of the early images with you. So this one, I didn't pick the one right over the North Pole because the features of the North Pole are so alien compared to what we're used to seeing. So you can see near the bottom of the picture, you can still see some of the belts and zones there that actually makes you realize this still is Jupiter. So this was, remember I told you about 2 hours pole to pole, so we're not quite over the pole at this point since we're 2 hours away from closest approach. But you can already see the colors change. We see greens and blues. We see an incredible amount of storms. So the mechanisms that are operating here for the North Pole are a lot different than they are for the rest of the planet. And this is going to be fascinating to sort out. This is the South Pole, so here we are 1 hour past closest approach, right over the South Pole. And again, this looks like an alien landscape. If I didn't tell you this is Jupiter, you'd probably say that's not Jupiter. It doesn't even look like Jupiter. But you can see the incredible storm formations there. There's a little bit of a belt and zone structure, but it's different than the rest of the planet. And we're going to have a lot of fun sorting through this and trying to figure out why is this so different at the poles. This is a never before seen perspective because none of the spacecraft that flew by ever had an angle on the South Pole. So our North Pole and South Pole images are first time we've ever seen that. Our infrared camera took this incredible picture of the southern aurora, and it almost looks like it has depth. So this is taken about 4 hours after closest approach. Again, unprecedented. Nobody's ever seen these shots before because no spacecraft has ever been here before. This was taken with our infrared camera. And these were as well. You're going to love this. Remember, infrared is heat, just below visible wavelengths. So the top channel shows you the aurora, and the bottom channel is focused more on the hot and cold spots. Remember, we can only see the aurora with our ultraviolet and infrared cameras. So you can see there's an incredible variation on the lower screen. There's the great red spot. There's incredible variation in how much heat is coming out. So it makes the theory about the Galileo probe very plausible that we may indeed have hit a hot spot because certainly the atmosphere is not well mixed at all. So it's going to be interesting to see how far down we have to go before these features start to blend and change. You're going to like this too. These are Juno cam images as we approached Jupiter. Someone else saw something like this 400 years ago. His name was Galileo. These are the actual Galilean moons that Galileo first observed back in 1610. He thought they were stars of Jupiter. It didn't take too long for him to figure out that they actually were orbiting around Jupiter. He got a little bit of trouble espousing that theory with the church. But this is mind-blowing. You can see the sun is to the right. This was taken over a 17-day span. First time we've ever filmed celestial motion of moons orbiting a planetary body. Io, Europa, Callisto, and Ganymede. It's been an incredible journey. I've been working on this project for 10 and a half years, but we've also had some incredible partners. I want to mention just a few. The principal investigators, Home Institute, is the Southwest Research Institute in San Antonio, Texas, and they provided 2 of our 9 instruments. Jet Propulsion Laboratory, just up the road here in Pasadena, is where we manage the development and operations of the mission, and we provided 2 of our 9 instruments. And the other key partner is Lockheed Martin. They built the spacecraft, integrated the instruments, and form the core part of our operations team right now. And of course, the master partner, NASA. Without NASA, none of this would have happened. So we encourage you to follow along. As I said, we've just started the really fun stuff. We have 32 science orbits starting in November. On October 19th, we'll fire the main engine, reduce our orbit to 14 days, and then the fun begins. You can follow along at the Juno mission website, and if that's too long, you can just type in missionjuno.com. We also got that URL. Or you can follow along on the NASA website, nasa.gov/Juno. And thank you for coming. And if there are questions, I'll be happy to answer. Most of them.
What do you do with the spin rate and the attitude during the perijove passes?
It's actually pretty stable.
So you don't spin it down and
No. Most of the missions at 2 RPM. We only spun up to 5 RPM for the main engine burns. So, of course, the engineering team, being engineers, track it to a gnat's eyelash, but we really see very little fluctuation in the 2 RPM spin rate as we fly by. So we actually stay facing the sun through the whole time, and it's a nice, simple concept. Helps keep the cost down, which is also good these days.
Is the Waves instrument the same as been flown on previous spinner instruments? Such as Wind, and I think Themis had Waves instruments on it?
They had similar versions, probably from the same place, University of Iowa. It's very rare. You don't see many spacecraft spin. Galileo did have a spun section, but other than that, it's pretty unusual. But the chief scientist on Waves also worked on Voyager, and so we have a lot of scientists that have flown on many other missions as well. So, good question.
You mentioned a potential extension of the mission.
Thank you. Yes, I have to tell you, it's really difficult when, most of us at JPL have worked on lots of missions, and they all get extended, and then you come over to Juno, and the first time I saw that, I was like, are you serious? We're really going to deorbit? But the planetary protection requirement is a pretty serious one. You really can't go around that. Or can you? So our team came up with a very creative idea that meets the planetary protection requirement without deorbiting. So let me explain how that works. Remember, the planet bulges. It's oblate around the equator. But our orbit rotates. That means the atmosphere is getting closer to the planet enough that we can, once we've gone 36 orbits, we can lower our altitude to about 1,500 miles above the cloud tops. That's actually below the bulge. And then about 5 years later, we'll come around to the fat part of the planet and deorbit. So that's a great concept. We've done analysis that indicates it should be viable from a controllability perspective. It should be viable in terms of planetary protection and not hitting Europa. But at this point, it's just a concept. We still have a lot ahead of us. If everything goes well, and of course, we really design these spacecraft with a lot of margin on purpose. And so we like to cash that in and get a few more months at the end. We'll see how it goes. We'll pick that story back up in 2017. Thank you for reminding me.
Is there one more?
So curious as to actually see what's inside of Jupiter. Has there ever been any thoughts about trying to do some imaging inside and through those clouds, maybe with synthetic aperture radar or something?
Well, you will get some of that from our radiometer. Our radiometer is half of a radar. We just don't have the transmitter. But in a way, we don't need the transmitter because Jupiter is the transmitter. And so the 6 channels that we get, and the way the instrument was constructed, this radiometer was designed specifically for this mission. So nobody's ever flown a radiometer like this before. And remember, since we're spinning, we will get a lot of look angles, which is how synthetic aperture radars work. And so we expect we'll be able to create some very interesting visualizations of what's happening at different levels. So I can hardly wait. It should be very interesting. I honestly don't know how they do it. When I talk to the scientist that runs that investigation, all the models and the way they cross-correlate everything, it's really, really impressive. There's another one back there. Oh, that was the last one? Well, there's more. Okay.
Well, again, I would just like to invite Jim Mazur up. I think he's here to present a certificate of appreciation to Rick. And again, thank you all for being here. So, Jim, over to you.
Rick, for you and Scott and the whole JPL team on behalf of AIAA, we just want to congratulate you on a great beginning of a mission and wish you a lot of good luck on your rest of your science experiments that are to come. Hard to believe you had to wait 5 years just to get started, but from what you've shown, it's well worth the wait, and I think we're all looking forward to seeing the results. So thank you very much and congratulations.
Thank you. Thank you. It is. Thank you.